这个得20个，然后这个要找到一个这个 value 嘛，这个0是还是这个4是？
这里是零，所以是零，这个写错了，好像有改的，是吗？等一下，好像有人告诉我这个东西，6点几来的，
第9章
9，
5.1。
对，应该是零，这个4写错了，
哦，
因为这里是零嘛，嗯，等一下9章，对哦，
还有一
该
个，
上涨，
哎，也是5.3是1.2.4，
对的，
嗯，
这个
5.3但挺6，
六啊，
嗯，
这一个的话，你要找什么？
是这个大等于5的
这个什么？
然后-1.20和-1.02，我记得好像
你可以选这两个或者选这两个的。
这样。
嗯，PVP 的什么？你可以选这两个嘛，这两个，
嗯，
你怎么选出用这个？
这个是算术，哎，对，那等于5的话，再你然后
不用带啊，因为这个就是用他们的 eigenvalue 做出来，这个是 lambda 5的，这个也是 lambda 5的，是 lambda 4。那你算出来也是一样，
但是这个
但是这个应该是算错了，我估计应该是错的，因为他给的是这个。
算好几遍都是这个。
确定？哦，OK，可能他这一个是用这两个造出来的，是吗？这样，这个乘5过后加这个，对，他这个是用这两个造出来的啊，你可以这样找，但是他的题目就是要你直接从这里找出来。对，你知道这个他怎么造的吗？他的 S2是5，SE 是1，
啊，
对照出来。嗯，对，嗯嗯
嗯，
嗯哼，什么？
那个那个答案是
嗯不然等一下我们讨论这个。你可以 screenshot 发给我听，我们直接在班上讨论。
那个亲
对，
戚，
发听，
还有这个我也不太明
也可以发给我，发给我。很多人都在问这两题，你发给我，直接讨论。哦，you want the quiz? Yes. Okay. You need to return me like that. Yes, yes. Interesting. Okay. I'll post the solution as well. Yeah, yes. Yeah. Hello. Right, today is March 14, 3.14. So happy Pi Day. Okay. Yeah, so I think before we share new stuff, let's do some stuff related to your quiz. I think a lot of you have some similar question. So let's discuss some question from your textbook. This is from 6.1啊，我知道6点几啊，这个 6 point so that you can go back and refer 6 point 5点10 OK 5 point 两个都是5点10对吧 OK 5.4.4 let's do this first. I think quite a lot of you have trouble understanding associating a matrix to a linear transformation. But I think this is natural because this is the most abstract part of this course. Learning is like this, so you get stuck, you unstuck, you get stuck, you unstuck. So please get used to it. This is a natural process. Okay, first of all, I found that some of you don't even understand what a linear transformation is. Right. So what's a linear transformation? What's a linear? What is it? Tell me the keyword for linear transformation. Hmm? What's the keyword? Start with F. Function. Function. So it's a function. What is a function? Function is a what? It's like a machine. You feed it something, it give you something. You give an input, it give you an output. Okay. So if you want, you can think about T like this. Okay, you give an input, and then T give you an output. Not like a machine. Okay, if you like machine more than a function. Okay. And then linear more than that, right? For linear transformation, it's more than that. There are two more properties, right? What are the two more properties? Two more properties. Sorry? Okay, not close, preserve, right? Preserve, because tx plus y equals to tx plus dy. And then one more thing is preserve. Scalar multiplication, good. Tcx equals to cdx. Okay. So, well, we define, so this is a function between vector spaces, right? So we should automatically check whether this is a linear transformation or not. In fact, the first question is ask you to check first, this is a linear transformation or not. Okay. In fact, this is the first thing the question wants you to see. Because if we write down a map between vector space, which is not linear transformation, is almost useless. Yeah, almost useless. It's just a normal function. So we want to see whether it satisfies these two property or not. Okay. Yeah. So let's try. So first, we will take two vector in P2. Okay. And then, so the vector here, instead of putting x and y, right, let's put p and q to signify that it is a polynomial. and you will do TP plus TQ. Okay, so you want to show that. Can I put WTS? You do know want to show? Want to show? Okay. So here I'll put want to show. Okay, maybe just put goal. Don't want to teach you new word. Okay, our goal is to show that TP plus Q equals to TP plus TQ. Okay. So to show that some things are equal, right, you need to start from one way to the other way. And you can start both way also, right? Last time I told you. You can start both way. Right. Yeah, so what's going on here? Let's see. So these are polynomial in what variable? If you see from this notation here, right? Okay, what's the variable you use for your P2? You recognize from here, no? Use T, right? Okay. Why? Before even checking this is a linear transformation, right? You should see that they go to the right places, right? So if you take in degree at most 2, does it split out degree at most 2 or not? Can you see whether this output here is a degree at most 2 or not? Why? Why? Why is it degree at most 2? Hmm. Hey, yesterday I met a FYP boss, not FYP boss. My FYP student go and do an internship, and then we need to like interview the boss, give feedback on our student. And you know what the boss said? He said, "Oh, my student, every time told me understand. When she go to present, I cannot explain, not explain. Hey, this is workplace. This is not school. Not uni. If you cannot explain to me, maybe I still give you mark. If you cannot explain to your boss, I don't know the boss want to give you salary or not. You understand or not? Okay, so make sure you know how to explain the things you know. Even if you don't know, you should also identify what you don't know. The boss said, I'm very angry about the student because he didn't tell me what he don't know. Every time he tell me he cannot present. It's a very serious issue. It's not just in class. You cannot explain to the professor or student. Again, this is to boss. Boss control your salary, by the way. Yeah. Okay. So this is a real issue. Okay. So, well, come back here. So TP going to this polynomial here. Is this a polynomial or not? Do you understand what is P0, P1, P2? You understand? What do you understand? What is P0, P1, P2? Are they polynomial or are they number? Number, right? Okay, because you do substitution. So for example, let's put an example here. Okay. So if I apply T to a polynomial, what's your favorite polynomial? Let's say 1 plus T. Okay, so what does P0 did to 1 plus T? You substitute T as 0, right? And then for P1, you substitute T as 1. And then times T plus 1 plus 2 times T squared. Okay, so how do you see these? Actually, uh, this definition of T could be more complete. That is, I put TP little t here. Okay, so this is what it actually means. So you could see that if you compare PT to P0, what happens? You just substitute T as 0. Okay. Okay. Yeah, another thing is, I'm not sure, are you familiar with constant function? So for example, What happens if you apply to a constant function? Let's say constant function 2. What is P0 there? Sorry? Hi, Bryson. Sorry? 0. You think 0 like this? P1? Or P1? Is it 0? You say 0. P1? About P1? So here we take Pt equals to 2. Okay, so if you say P2 is 0, how about P1? What do you think? Can you give me answer? Try. Never mind. Wrong is okay one. The most important thing I think we learned in Chinese primary school, 知错能改，善莫大焉. If you can change, it's fine. You cannot say I do wrong only lah. Never mind, already wrong. You must change if you are wrong. Yeah, like P1. 2. P1 is 2. P2 lah. P2 is 2. You want to change your answer for P0 no? Wait, not yet. I haven't finished yet. Let me deal with him first. How about P0? You want to change answer? You want to keep it at 0? Yes. Okay, can you tell us your logic to find this 0 to 2 number out? Can you tell us your logic? Wrong is okay, we won't laugh at you. Everyone learn together. Can you tell us the logic? Don't know? You just guess. Okay. Okay. Hiba, what did you want to say? You don't get why P1 is 2. How do you know P1 is P2? But you agree with P0 to be 0? You also don't know. Okay, so you have question for 3 of them. Sure. So, well, when we put T2 here means what? This polynomial is 2, but this polynomial is 2 means what? You see, P2 equals to 2. There's nothing on right hand side about T. So meaning what? No matter what I put, yeah, it's always 2. So in this case, what should P0, P1, P2 be? Always 2. Okay, so it's always 2. So it should be 2 here. Okay, this is what it means by constant function. You can think of this variable as time variable. So no matter what time, it is still constant, still the same number. Okay, previously, what does it do to the time? You do plus 1, t plus 1. Okay, you plus 1 to every time. Okay, so there's some reason we put t here. You can think of this as a time function. Okay, so do we have a better understanding on this function now? Okay, so let's do this checking of linear transformation here. Okay. Okay, let's do checking on the linear transformation. So let's start on one side, TPT plus QT here. Okay, so what is this? This is equal what? Can you apply the formula directly or not now? Can you do it? You can't quite do it yet. Why? Let me copy down the formula first. Okay, so this is the formula for your linear transformation. So you can't quite apply t on the sum of these polynomial yet. Why? Because you only know how to apply t to one polynomial. But how to combine two polynomials into one polynomial? What's the definition of addition of two polynomials? Anyone know? I think I briefly thought about this, but I guess maybe too brief. What's the definition of addition of two polynomials here? This thing is by definition p plus q polynomials. Okay, so this one is by definition means what? You cannot ask why, because it's definition. We define it to be true. Okay, so this is something that you don't know why is it true, because we let it to be true. That's all. Okay, different definition will lead to different story. Okay, but I can show you later what does it actually means here. So if we have this definition here, we will write T P Q. And now then you can see that, oh, this is a one polynomial like this. Then we can apply the apply the linear transformation formula. Okay. And then what to do next? The only thing you can do is apply the definition again, split it out. Okay, you split it out. Maybe you can follow first, later I'll tell you what this definition is trying to do. Okay, but remember what's your goal? Your goal is to split T on P plus Q to TP plus TQ. So let's write down the goal. But by definition, what's this? It is P0 plus minus P1 T plus P2 T squared plus Q0 minus PQ1 T plus Q2. Okay, but can you see that this second last line here and the third last line here is the same, just by commutativity. Okay. No question? Okay, so maybe I motivate a bit. What's this definition trying to do? Seems a bit stupid, but actually it's not. So for example, let me give you, for example, PT is 1, right? Then QT, let's say it is, let's say, what do you want? Maybe 2 plus T like that. Okay. So the question is, what is PT plus QT? Okay, so the question is this. Well, if you first write down PT plus QT, you should have 1 plus bracket 2T like that. But I don't think this is what you do in high school, right? What you do in high school, you directly combine them, right? So in fact, you are right now 3 plus. And then this is what we call P plus Q. Okay, can you see a difference or not? Can you see a difference between these two? You see, the last one is already in terms of T and then everything combined nicely. But the previous one is split. So this is the difference between these two notations. Okay or not? Huh? Max abstract or not? Is max abstract? Abstract or not? This is the real thing we are looking at. You understand? This is the exactly what's happening. Why we call a new name here? Because we want to differentiate these two guys. Although in the high school calculation they are the same, but you can see they are different or not. One of them are split the two. Understand? Okay. Yeah. Yeah. Okay. Okay. So this is the difference between PT plus QT and P plus Q compared to T. Yeah. So this one is for linear transformation, right? So is it okay? I left you to check the preserving scalar yourself. Anyone have problem showing preserving scalar? Or you want me to do here? Let's let you do it. Yeah, let's go to the next one. So preserving scalar. Left. More. Okay, let's do the which one? The next one is about eigenvector. That one you can do yourself, right? Eigenvector. Okay, let's do C. Let's do C. C, I think a lot of you asked me about it. So let's do C. So B is about eigenvector. If anyone want me to do, we can come back here again. But let's do C first. So C is find the matrix for T relative to the basis 1T squared. Okay, so before we want to do this question, right? Do you know what is the concept governed behind this? Question here. Matrix for T means what? Matrix for a linear transformation. What's the relation between matrix and linear transformation? What's the concept here? What's the concept here? Every linear transformation. So this is the line you need to remember. This every linear transformation between finite dimensional vector space is a matrix transformation. So you can write every transformation as a matrix transformation. Okay. Although you didn't see this real sentence inside your lecture notes, because in the lecture notes we just say that vector space with dimension n. With dimension n means what? It is finite dimensional because n is finite. Okay. 100 also finite. 1 million also finite. 10 billion also finite. Okay. Although the number is very big, still finite. Okay. Okay. So what to do here? So let's draw out what you have. I like to draw, right? So please draw. So take P2. P2, you have a map T. And then what does this map do? So let's write down. Let's record it. I think it's better you learn this kind of arrow drawing. It's very convenient actually to record everything you have. So PT will send to P0. Let's forget about the arrow. I don't want to draw the arrow, vector arrow. P0 plus P1T plus, sorry, not plus, right? It's minus, and P2 is squared. Okay. So previously we have shown that T is a linear transformation, right? So there should be an associated matrix transformation. But you know that what does matrix need to multiply to? What does matrix need to multiply to? Makes sense. What does, okay, let's say m times n matrix. What does it need to multiply to make sense? N times one factor or n times some size of matrix, right? Okay. But in this case here, we will care about R3 here. Okay, we care about R3 here. How do I get the number 3? Anyone have ideas on how to get the number 3? Huh? Right? How do we get the number 3 here? The question still got one information, right? P2 is a span of 1 T and T squared. But what does this mean? What does this mean? This is very important. 3 basis elements, right? 3 basis elements means what? Every element in P2 can be expressed as a linear combination of 1 T and T squared. Not just express, this is unique. This is unique. Unique, right? Unique. What's the map? What's the map? So here is unique. So let me write down here. PT can be written as C1 times 1 plus C2 times T plus C3 times T squared. And then C1, C2, C3 is unique. And what's the way we collect this information? C1, C2, C3. What's the name? Coordinate vector. Okay, so this is the coordinate vector. So going down to R3, what we use is coordinate vector. Let's call this span. Okay, coordinate vector here. We get C1, C2, and C3 like this. Okay. And similarly on the other side, we also have this. Right. So you see, if we follow this logic, right? You see, if I already write PT in terms of C1, C2, C3, so can I find what's the image in terms of C1, C2, C3? Do you know what to do? Can you see what to do here? You just substitute your T as 0, 1, and then 2. Figure out what is this. Okay, let's figure out what is this. So P0, you only left C1 minus C2 plus P3, T plus P2 is what? Okay, do you have C1? Yeah, you have C1 here. C1 plus C2 plus C3, and then P2, C1 plus 2C2 plus 4C3 T squared, like that. Okay, but if you read out the coordinate vector, what do you get here? You get C1 minus C1 minus C2 minus C3, C1 plus C2 plus 4C3. Because you read out the coefficient in front of 1, T, and T squared. Okay, so now the question is, you see, you have two vectors here. So now the story is about this M here. So what do you call it? What do you call this matrix here? Maybe you could call it M subscript T. Okay. So do you think there's a matrix you can put here to get from this C1, C2, C3 to the other side? Do you think so? Or maybe you can guess it. Maybe you can guess. Okay, let's say if I'm gonna put an MT here, what's the size? Yes, the domain is 3, right? 3-dimensional. The codomain also 3-dimensional. So it should be a 3 by 3 matrix. Can you figure out what 3 by 3 matrix you can put here? For example, how to get C1 only out of these 3? What's the row you need to multiply here? 1, 0, 0, right? Because we want to kill C2, C3. And then you want -1 on all of them. So you put -1 on the whole row. Last one. 1, 2, 4. Okay, so this is one way to figure out. But there's another convenient way to do this actually. Did you recognize how we get this number here? How to get this number? to get this number. So one way to see this number is to look here. You can see it vertically. What do I mean by this? Did you see there's a formula inside your lecture notes? What's the formula for this M here? Anyone can recall what's the formula inside your note? Coefficient with transformation. Yeah, so you apply T to what? Good, 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 very good. So actually, in general, you apply T to B1, and then you apply T to B2, you apply T to B3. Where are these B come from? These are the element in your basis. Good, very good. Basis of what? The domain. Okay, the domain. And then you need to interpret it in the basis of the codomain as well. But in this case, they are the same. In this case, they are the same. Okay, B and C is the same. Right, usually we call the basis for codomain C, right? But they are the same in this case. So you see, if you apply T to 1, okay, if you apply T to 1, apply T to 1 means what? The C1 is 1, C2 is 0, C3 is 0. So if you read this map vertically, you can see 1 minus 1 and 1. No, no. Can you see? 1, 1 minus 1 and 1. Okay, if you just consider the polynomial 1. Right. And then if you consider T, what happens? C1 is 0, C3 is 0, C2 is 1. So if you look at this vertically, first one, you don't have C2, so 0. And then this C2 is negative C2, so negative 1. And then here is 2 times C2, so become 2. Okay, now. And then similarly for the last one, T3, which is the T squared. Understand or not? Okay. If you cannot memorize this, at least for our course, I think you can just see the matrix multiplication. Okay. But if you could imagine we have more dimension, right? It's not as easy you can see this anymore. Because you need to compute a lot. Okay. And then this is a better way to compute. This is the better way. Okay, why is this the better way? This is like a vertical way to see the map. Kind of vertical. Vertical, right? I don't know. Is it vertical to you? Do you think this is vertical? You think so? Yeah. So maybe you need to like how to say, arrange it in a proper way so that you can interpret it better. Yeah. Because why? Because we really see these 1t and t squared as a different basis. They are different bases. Because we say that they are linearly independent, right? Okay, so yeah, they are different. Okay, 洛奇. Okay, no, you got other questions? No. Okay. Yeah, I think there's one good way you guys learning is you check whether you learn or not. How to check? You do question. Okay. You say, oh, I think I understand what teacher said. Okay, go and do question, and then get start. Okay, then learn from where you start. Then because the place you start is reflecting what you don't understand already. You think that you understand, actually you don't. So this go back to the story of my student going to internal. He thought he understood, but when people ask him, don't understand. So you have to keep going through this kind of process inside university one. If you don't go through in university, you also have to go through inside the society. It's the same. So why not do it now? You understand or not? Now it's low risk. You understand what is low risk? 你懂吗 ？Low risk. 下面有什么风险 ？When you go up, your risk is your life. You know, your risk is your life. Now it's just CGPA. Okay, so make sure you learn it in university. Okay. Yeah, next. Go to the next one. 5.4.8. Let's do 5.4. Yeah, 5.5.8. So this question it says that find the B matrix for the transformation. So this transformation is sending x to ax, where B is B1, B2. Okay. First of all, you see this transformation is a matrix transformation, so automatically a linear transformation already. Okay, because we say that every matrix transformation is linear. And then did you notice this arrow here? I think if you notice, I draw a lot of time. You recognize what's the difference between this arrow and this arrow, for example? What's the difference? There's a hook on the other one. But why we use a different arrow here? You see why? Yeah, let's write down an A first so that we can identify this. So let A be so 4, 3, 3, 2. Okay, so what's A doing here? A is a 2 by 2 matrix. So the matrix it takes in is R2 and then spit out is R2. Okay, so what's the difference between these two arrows here? The first arrow we will put here is for spaces, okay, for the domain and codomain. But for this hook arrow here, what we put is element. Okay, so this is the difference. Okay, now, yeah, so this is the difference. So if you want to put arrow for elements, we'll put a hook. Okay, and then if for spaces, we just put a normal arrow. Okay, so let's write down the arrow again. I think this is a very good language to learn. So maybe you should learn it. Okay. And then what's the basis here? So let's write down the basis. So on both sides, this is the span of B1 and B2, which is 3, 2, and minus 1. Okay, so what does it mean by finding B matrix for the transformation? So this question further understand what is this matrix of a transformation is doing. Okay, so what is this trying to say here? Okay, so what's this trying to say here? Well, similarly, once you have a basis, you should be able to express all your vector in terms of these two bases here. I mean linear combination of these two bases. Right. Okay. And then you apply A. Okay, you apply A to this X here. Okay. But let's say I give you some example here. But I mean, how do you compute this AX actually? In real life, how do you compute this AX? How to compute in real life? In real life, how to compute? The usual matrix vector multiplication, correct? But now, since you know how to split X into these two vectors already, why not just compute A of these two vectors? I just need to know what A happened to these two vectors. You don't need to do the general one. You get what I mean about? You get what I mean? So you see, instead of doing the row column multiplication, right? What you do is I just need to ask myself, what does A do to 3, 2, and minus 1, 1 is enough? I just need to know the answer of these two. Why? Because this is a linear transformation. I can just let A add on 3, 2, and A add on minus 1, 1, because I can pull all the scalar out. So the question is, I just need to know A apply to these two basis elements. That's it. Why? Because later this C1, C2 will just change if we know how to express X in terms of these shapes. So I don't need to do like row column configuration every time. I just need to know A, what does A do to this two vector, basis vector. Okay. Okay, no. Okay. So, but this is equivalent to what? Okay, so this is equivalent to what? Should I do it for you or should we continue? Do you want to see what A do to these two vector? Do you want to see or not? Want to see? Okay, let's do it then. Right. So I think this needs some computation here. So I need to do it. So when should I do it? Let's do it here first. Let's see, we will move it later. So A 3, 2. So this needs some time. Maybe you can compute together. And then A times. Can anyone help me to compute? Need some time. Is it correct? Correct or not? Which one? First one is 5 and 0. Let me see. Oh, yes, you're right. Second one, correct or not? Okay. So maybe you write it in this way. Okay, but this information is not useful. It's not useful. Okay, so what we need to do next? Actually, we need to express 5, 0, and 5, 5 in terms of the basis element again. Okay, so can you quickly see or not? Can we do by inspection? Can we quickly see or we need to do the augmented matrix stuff? Can quickly see or not? Anyone can see by inspection? So how to add these two together to get 5, 0? For sure, you need a negative because the y, the second coordinate are both positive. How to create a 5 here? You need to make them equal, both of, so this need to multiply to 2 first. Depends. So I need to make 5. How to make 5 from 3 and minus 2? Okay, never mind. Just solve it. Solve the augmented matrix. So we need to solve the augmented matrix. 3 minus 1, 2, 1, and 5, 0. And then the other one is 3 minus 1, 2, 1, and 5, 5. Okay, solve these two. What do you get? What's the raw reduced echelon form for these two? You compute, you tell me. Maybe one side do one. What's the raw reduced echelon form for these two? First one. Okay, what do you get? 1 negative 1 0 0 1. Okay, 1 and negative 2. 1 and -2. Okay, makes sense, right? Okay, 1 and -2, so you get 3 plus 2, and then 2 minus 2, 0. Okay, good. Next one. Next one. I think I can guess this already. So it's 2 plus 2 plus 1. Can follow? Follow? Okay, 2 plus 1. Okay, so it means what? If we're gonna further split this, C1 times what is 50 here? 1 times 32 plus, sorry, minus 2 times -1, 1. Okay, plus C2 times 2 times 32 plus 1 -1, 1, like this. Okay, so if you expand out, what do you get? So you can see that the coefficient in front of 3, 2, and 1, -1, 1 change. Change to what? So here becomes C1 plus 2C2, and then -1, 1 becomes what? -2C1 plus C2. Okay. So can you see or not? Can you see the coefficient in front of C2 and -1, 1 change under this map here? Okay, instead of doing the row, column, row, column, row, column multiplication, right? What we see here is just the coefficient change in front of the basis element. Okay, so now the matrix B that associate to A is trying to keep track how this coefficient change. Okay, why the B matrix can keep track the coefficient change? Because remember, what does the coordinate vector do? Or remember, what does the coordinate vector do? Copy this here. Maybe we paste the last answer here. Copy. Wait. Okay, so you can see that the basis element won't change one. It won't change. What's changed is the coefficient. But how do we describe things that happens in coefficient? We can just look at the coordinate vector of the basis. But in this case here, it turns out that the coordinate vector gives you the space of R2 also, because there's only 2 coefficients, right? Okay, so you can see that if you do this, what does coordinate vector do? Forget the basis element. I just keep the coefficient, right? We just keep the coefficient. So under this mapping, we'll get C1, C2, okay, in the codomain. How about the other side? Our coefficient change based on the calculation just now. So what happens then? We get C1 plus 2C2, and then minus 2C1 plus C2. But you see, your starting point is a vector. Any point is a vector. And then you go through a linear transformation. So there should exist some matrix here. Okay, there should exist some matrix here. So what do you think? What's the matrix we can put here? Get a name for this matrix, AB. Put it AB. What's this matrix here? I mean, from here, you should also guess, right? What's it? 1, 2, and -2. What? Okay. But in general, how to see? 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 You apply A to B1, and then read out the coefficient, coordinate vector, and then you apply A to B2. It's the same as what we did for T just now. But can you see? See again. Look at this closely. Apply A to B1. read out the coordinate vector. Apply A to B2, read out the coordinate vector. Hey, isn't it what we did just now? Apply A to B1, apply A to B2, read out the coordinate vector. This is what exactly we did. You understand now? Okay, so this formula actually follow this line of logic here. Okay, why we want to do this? Because we want to skip all the different matrix row operation. Okay, so we turn the question of matrix vector multiplication to express your vector in terms of bases. That's all. As long as I know what is C1, C2, I can get the solution out already. You can see the difference or not? Can you see the difference? Instead of doing the matrix vector multiplication, as long as I can express my vector in terms of linear combination of the two bases, the C1, C2 scalar, I know I can straight away get the answer using this formula that I get. Okay. Do you think it's better? Better or not? No way. No. No way. Why do you think no? Why do you think no? Can you give some reason? So many working, but you see, this working is how to say? Okay, 1, 2, 3, 4, 5. Maybe this working is a lot, but you need to imagine. You need to imagine if you have a size of 100/million, or maybe put a billion here. How do you do this matrix vector multiplication? You need to do how many times? How many times you need to do? And then if you need to do it for all x, for all x, or how many x? Infinite x or here? You understand or not? But now I only just need to check on two, or maybe depend on bases, number of bases. And then here, how to find this? We just do row reduction. We can find already. You understand or not? Depends, depend on the size. Okay, depend on the size. Yeah, depend. Maybe one is easier than the other. Okay. Depends. Yeah. Yeah. So if we're gonna use this way, right? What we need to know is how to express your x in terms of the basis element first, and then you go through this formula. You can find it. Or you do the traditional way, just compute, give you an x, go ax, compute x, go ax, compute x, go ax. Okay, now. How to say? Yeah, because if you just like that compute like a label like that, keep computing, then you cannot see what's really going on. But this is what's really going on. And then this can be generalized to other vector space. Computation is very specific to vector space. If you are in this Rn, maybe you do matrix vector computation. If you are in the polynomial space just now, then you do different computation, right? But this theory will work for all vector space. Okay. Yeah. Okay. I think there's one thing you need to make up your mind, change your mind. Since you have a chance to do learning in university, right? I think you should learn higher knowledge. Otherwise, you could just go and take diploma, or you can just go to do technician. They are really like 傻傻做 like that. Just do it. Don't know what they are doing. It's like worker, like how to say 你们中国人听不懂什么叫傻做吗？听不懂啊？我不懂啊，我家里人是说傻做啊。I mean，你们也不是。OK，maybe 有人 get 到我什么意思？不懂，就是it's like you do without knowing what you are doing. You just do it. 你们叫什么？傻做呢？你是哪里人？你是中国哪里人？你听得懂吗？你是中国哪里人？哦，你南京，哎，这样也不错，我是福建的，我还会只有南部听得懂南部话吗？OK，还是南部也听不懂。 听不懂哈？Yeah，想不到南京人哦。OK，很好。So it's like doing without knowing lah, because you already come to university ma. I think it's better you learn some higher knowledge, even though you don't apply lah. Maybe 你去买奶茶的时候没有用到这个东西。But I think it's better you keep this knowledge in your mind so that you can think differently toward a problem. OK 吗？Yeah，肯定会好过那些没有上大学的，yeah，对不对？OK，Yeah，So OK 吗？洛奇，还有问题吗？有问题吗？可以问的，可以问的，不要紧的，可以问的。You can ask if you have problem. Any other question? We already take out 1 hour. It's okay. You have other question? No question. Quiz. Prepare very good already. um. Okay. If no question, right? Maybe we go for another 15 minutes. Then I give you a break. In this 15 minutes, maybe I go through some application of what you have learned before. Maybe you don't need copy. You just listen. It's fine. And I don't want to write also. Actually, this is about chapter 7. If you gonna use linear algebra in your field, right, in your degree, I think it's better to go through chapter 7. Because I know some of you are from the computer side. Although you don't test on it, but maybe it's worth to go through a little bit. And I also will put out the notes for you in case in future you need it. So there's no exam question from chapter 7, so you don't need to worry about chapter 7. And then the exam is almost, I cannot say exactly the same, but it's from chapter 1 to 6, which we tested you on quizzes. And there are 6 questions. Every time people will ask me how many questions. But question number really not important. Even if I put 1 question, I also can make it 2 hours for you. Correct? No? There's no, I mean, you have to like believe in your lecturer, believe in professional. Even if the lecturer put 10 questions, what can you do? I ask you, what can you do? You think you can change the paper? Man? Cannot lah. Obviously, we already print it out. So there's no use of asking it. So what's the use? What can you do? Okay, the question comes back, what can you do? You can only understand everything. That's all. That's the only thing you can do. Don't think that you can alter the question paper. It's impossible. Okay, it's impossible. Okay, so we will make sure that you can finish it in 2 hours. That's all. Okay, so the number is really not a very important thing. Okay. Okay. Question 7. Chapter 7. Chapter 7 is about symmetric matrices and quadratic form. So there are 2 things actually. 2 things here. So quadratic form is more geometry. Symmetric function. So what's symmetric function here? So let's define what is symmetric function. So symmetric function is a matrix which satisfies AT equals to A. Okay, the last time you talk about AT is what? You talk about orthogonal matrix or autonomous matrix. Autonomous, right? You need normal actually. Right now you need normal because you need the 1. Okay, if you have a matrix which has autonomous basis, AT is equal to the A inverse. But now this one is more straightforward. AT straight away A already, not the inverse. Okay, AT is A. So do we have examples here? For example, this guy here, AT equals to A. Okay, so you can see that it's symmetry across the main diagonal here because row become column still the same. Okay, so it's symmetric along the main diagonal. If it's AT symmetric, we'll say AT equals to minus A. And then this example asks you to diagonalize. Okay, without writing down the step, can you tell me what to do to diagonalize a matrix? This is a revision for you. Now what do you do first? What do you do? Yes. What do you do first? Eigenvalue, yes. You want to find the eigenvalue, but how to find the eigenvalue? Sorry? Sorry, I cannot get. That A, and then lambda I. What do you call that? That's a polynomial, right? That's the characteristic polynomial. Okay, so you find the characteristic polynomial, and then you let it equal to 0, and then you find the root. Okay, after you find the root, what happened? Okay, you find the lambda already, lambda 1, lambda 2, lambda 3. So in this case here, at most 3 lambda, right? At most. Because some of them could have algebraic multiplicity more than 1. And so if you found the lambda I, then what do you do? Now what do you do? So you take A minus lambda I and then row reduce it and then get the eigenvector. So you find the null space of A minus lambda I. Okay, null space of the lambda I. So when is it like diagonalizable? When is it diagonalizable? If all the algebraic multiplicity equals to the geometric multiplicity. So if you have lambda 1 appear twice, you need to make sure that you have 2 linearly independent eigenvector. If you only found one, what happened? It is not diagonalizable. Okay? Sometimes it's not your calculation wrong, and sometimes it's just not diagonalizable. But you need to check your calculation, obviously. Okay, so this is what you did. And then secondly is, what's nice thing about this symmetric matrix? If A is a symmetric matrix, then any 2 eigenvectors from different eigenspace are orthogonal. Last time we just tell you they are linearly independent. But this time, automatically orthogonal already. Okay, if you have a symmetric matrix. But because orthogonal also imply linearly independent. Okay, stronger. Okay, stronger. Okay, so this is the nice thing about symmetric matrix here. But the proof is not too hard, actually. We won't focus on it. And next is, since all of them are orthogonal, right, we will say that the matrix is orthogonally diagonalizable, okay, because you diagonalize with orthogonal P matrix. And then the theorem is a square matrix is orthogonally diagonalizable if and only if A is a symmetric matrix. Okay, so this says that if you found that my matrix, my diagonalization built out by orthogonal P, automatically your A should come from a symmetric matrix. Or if it is symmetric matrix, your P should be orthogonal. Yeah. Okay. So what's the nice thing about orthogonality here? Because you write it in PDP inverse, right? Instead, this P inverse is equal to PT. Because you can make it orthogonal. Okay, last time we talked about orthogonal matrix. What does orthogonal matrix satisfy? P inverse equals to PT. Yeah. So you can see that P inverse is easier to find. You don't need to use the Cramer's rule. No need to use what row reduction. You just transpose your P. Okay. Yeah. So symmetric matrix will give you this advantage. Okay. Yeah, and then this is the same story. So another theorem is how nice is about symmetric matrix. It will always have n real eigenvalue. The eigenvalue must be real. There's no complex. I think if you do the tutorial question, right, some of the characteristic polynomial have solution in real. In complex, but not real. Correct or not? Yeah. But in this case here, it is always real for symmetric matrix. It's always real.
And then the dimension of the eigenspace for each eigenvalue equals to the multiplicity of, so the algebraic multiplicity of lambda. So meaning what? This sentence tells you what? Every symmetric matrix is always diagonalizable. Always diagonalizable. Because the geometric multiplicity and algebraic multiplicity is always the same. Okay. And then C, the eigenspaces are mutually orthogonal. Okay, just now we have it here. They're orthogonal. And then so A is orthogonally diagonalizable. This is by definition. Okay, so how nice is symmetric matrix? It always have n real eigenvalues. The eigenvalue always is a real number, and then you always able to diagonalize it. And yeah, so this is it. So another nice thing about this PDP inverse, right? You can write it in this form here. Okay, you can write it in this form, U1 times U1T. If you swap it over, it's a dot product, right? U1T, U1. Okay, but this one is U1, U1T. Okay. Not that you cannot do that to the general P inverse, because can you do that? You can do that, but there's no meaning to that. You just put a V1 inverse, Vn in V1T. But now here, what's the significance about this line here? That means you just need to know about U1, that's all. UI. And then what's concerning about this formula here, you need to know the lambda, you need to know the UI, that's all. You don't need to build this matrix even. You need to build this matrix. So this is a 1 times n times 1 computation. You don't need to do the matrix computation. These two really make difference in your computer. They really process these two things differently. In your mind, you also need to process them differently actually. Although we write equal here. Understand? No? Here, the first line is a matrix multiplication. Second line also matrix multiplication, but smaller size. But you do it multiple times. Okay. And then the input is a bit different. Is it? The second input is just vector. Vector in Rn. And then the first input is a matrix actually. It's different, no? Correct or not different? No? So these things are very sensitive when you deal with computer. You input a matrix, input a vector, actually is different story. Correct or not? I think you use computer, you know. But I don't use it. And then the last line here is what we call spectral decomposition. So if you heard about spectral decomposition of a matrix, this is what it means. Okay. What time is it? Okay, I could still got 8 minutes. Maybe we jump to the singular value decomposition first. Let me not show you the derivation first. Let me show you some magic. So the magic is this. Okay, so you see, usually when we do diagonalization, right, it's always a square matrix. But in this case, this is not a square matrix. This is a 2 by 3 matrix. But we also can split it into 3 matrix, multiplication of 3 matrix. So what's this 3 matrix here? You see the middle one is almost like a diagonal matrix, but got extra 0. Why? Because the original matrix is not square. It's not square. So you cannot really put the full square diagonal matrix here. But you can put a sub diagonal matrix here. And then multiply by 2 other matrix is like a diagonalization way to do things. But you can see that on 2 sides also different size. Because this is the nature of your A. Your A, the size of the, let's say the sigma here will be the same as your A. Okay. So you can see that What's the use for this? I don't know what's the use of this, but it's really cool. Why is it cool? If you go through this derivation here, actually it uses the idea of symmetric matrix that we say just now, and then go through these diagonalization way, okay, and then actually it involve how to say, where is it? Well, let me see. Let me find it. So basically for this decomposition, we call it a singular value decomposition. So it's not eigenvalue anymore. It's a singular value. But this singular value actually very closely related to eigenvalue. Okay, so the eigenvalue is referring to ATA. Because why? So there's a key here. So there's a key here. If your A is a, let's say just now is a 2 by 3 matrix, what do you think the size of ATA be? Okay, maybe let's figure out what is the size of AT first. What's the size of AT, transpose of A? 3 by A, right? Sorry, 3 by A. 3 by 2, right? Then if you do ATA becomes what? 3 by 3, square already. Okay, becomes square. So if it is a square matrix, you can ask whether it is diagonalizable or not. So if you go through this length calculation, right, it will involve ATA here. If it is diagonalizable, if it is diagonalizable, then you will split out a lambda I. And then what? And then you will keep your lambda I time this inner product between your VI, if you do this computation. If you look at how A act on the VI. But if VI length is 1, then you will just left with lambda. Okay. And what's the singular value? It is the square root of this number. Okay. So singular value means you have A, you apply to VI, okay, the orthogonal, the unit vector, and then you compute the length. See where the unit vector go. Okay, and then see what's the length of it. Okay. And then this number here, there's a relation between this number with the eigen value of ATA. Okay. Okay. And then use this concept to find this singular value decomposition. That is this theorem. Okay, so if you start with an m times n size of matrix, okay, and then you find the singular values like what we did just now, and then you can split your A into 3 matrices. I think I won't go through details, but I think I do it quite detailed in the notes. So if you're interested, you can read after you review all the exam content. Okay, this is about singular value decomposition. So we not only can diagonalize a matrix, but we also can singularly decompose a non-square matrix. Non-square matrix. Also related to diagonalization. The other part of this chapter is about quadratic form. So what's quadratic form? Wait, let me find a nice picture for you. Okay, so quadratic form is this. So if you look at this 4 picture here, okay, so what you notice here is they are surfaces defined by the variable square. Okay, with coefficient changes. Okay, so it's like a linear combination of x1 square, s2 square, si square, like that. Okay, so did you learn this in high school? No? Learn this in high school? No? Conic section stuff? No? Never? Okay. Anyway, calculus school, or you guys didn't take calculus? Okay, so basically this kind of linear combination, right, will draw out some surface here. You see, either it's a cone going out or it's a plane flipped. And then this one is a saddle. Like a saddle. Do you know a saddle? Have you ride a horse before? This is the one that put on the horse. And then the other cone is facing downward. Okay. In fact, In fact, we can write these as a matrix vector multiplication. Can you imagine how? Can you imagine how to write this as a matrix vector multiplication? Can you imagine? Yeah, this is the first break tool you need to break. Then we only can apply the knowledge we know. This is the first breakthrough we need to do. Can you write this as a, for example, let's just take this one. Can you write it as a some vector matrix multiplication? Can you imagine? Maybe I can do this. Let's see if this works or not. 3007. And then here multiplied by x1, x2 plus the other one. Nice. Okay, does it compute to the same thing? Correct, right? So in general, right, if I gave you a quadratic form, you can write it in this way. Okay, so basically you pull out the scalar into a matrix also. This is like what? The first chapter we did, right? We prove from the linear system how we prove the coefficient from the linear system. We put it into a matrix like this. Okay. And then surprisingly, if you know about this A, right? If you know about this A here, the eigenvalue of this matrix here, the eigenvalue of this matrix here will tell you how the shape looks like. Whether it's curved up, curved down, or it's a saddle. Yeah, surprisingly. The eigenvalue of the matrix that we pull out the coefficient will tell you how it looks like. Okay. I think that's all for this one. Okay. Any question or not? Other question on the exam or the course? Okay, so the plan for later is like this. So 10:30, we will take a quiz. And then after the quiz, if you want to leave, you can leave. If not, we will do a last overview on all the section you need to go through. And then I'll tell you what important section you need to focus for exam. Okay? Okay, let's take a break until 10:25.
人家招个还刚开始上课那个大家可以
OK 啊，我会 pause 我反正
看一下，然后考试出来。
可以没问题。
因为北汽什么？其实没有，我也不知道。
OK，你们
这个 B matrix 啊，其实什么东西？是它的那个
B matrix 啊，就是说这个 B 是这个 B 嘛，对不对？这个 B 是它的 basis，然后它的应该就是说，如果你把这个 S 写成这个 linear combination 过后，你可以把这个 A 看成在这个 basis 上面的作用。怎么看呢？其实要 go through 这个，你要看这个 A 怎么作用在它的 coefficient 上。
哦，不是，这个题目其实要找，它是找 B matrix。
要找 B matrix。
B matrix 是这个东西。
对，就是这个 matrix 会怎么样作用在 coefficient 上面？它作用在它的 coefficient 上面。
哎，其实有更简单的方式，
没有
直接找。
直接找就这个，来直接找是这个。你 A 作用在 B 完过后，找它的这个，找它的
coefficient。
对，没有错，
它出来了。
对，没有错。
上下
啊，上下对 ，OK， 对，所以是这样，其实你找的是这个 vertical 嘛，刚才我说就是这个 vertical， 这个吧。你看，你让 C1 等于1的时候 ，C2 等于0的时候就拿这个了。And then 你这个是让 C1 等于0 ，C2 等于1的时候，就是 A apply 去这个算出来 ，A apply 去这个算出来。
它的 coefficient。这样，对，这样。
干嘛？我听得懂也懂。
太好了。
对啊，刚刚我自己做的答案是吧？
诶，
是不是因为是因为我希望是这样子吗？我放这样子，就是因为题目它给的是有 negative，所以当 T 的时候它是减 T 是吧？还是减 T 吧？
对，现在是你这样讲这一排啊，这一排讲来啊，
因为你看啊，我这是我自己算的答案，因为我没有
你加算了，你加算了。
哦 T1的时候嘛，我的这里只有1，我的 P1就只有1哦。That means that means 我无论放0 1减
你会拿到1减 T 跟 T square 了，对不对？对，你1放在哪里？
我的1
你这边应该要写括弧 B 耶，你要写括弧 B 括弧 B 括弧 B 括弧 B 括弧 B，懂吗？因为不然的话，这3个是个 polynomial 来的，它不会长成这样子，它其实是要拿它的 coefficient 的。啊，对，没错。
感动了，可是你不要出
有信心了啊！
不要这样子讲，你不要这样讲。
我也 OK。那你真的很像我另外一个人。Anyway，不是你拿到1减 T 加 T 嘛，T square 嘛，对不对？Then 你怎么读它？
可是我不明白你，因为如果讲 P 1啊，that means 就是你的 PT 等于0A1 0啊，加就是总之这里会只有1吧哈。
对
啊，然后
你要1的话是，
那你无论放什么，你整排都是1啊。
不是，你还没有 apply T， 你要 apply T 给他。这样的话，你拿到什么？1减1加1 square 这样。
哦，所以是看这个哈，就是因为题目给我们这个，
因为这是 T 的作用。
我看成这个，就是它本来的
这个 P 罢了，你还要去 P，
因为 TP 这个，所以我们才放进这个里面，对吗？
对，这个是 T 出来的东西。
我是听你讲的，喂它，
这个是要喂进去的，你还没有喂，你就把它读出来了。
对，这个就是本来的 P2 transform 过后。
你这个是干嘛？这个？哦，这个 general。OK，
这个是 transform 过后的 P2。
对，没有错。
讲到没？
没有错。
太努力了。
你可以。
像这个是8题，它的 eigenvalue，就是应该是8004。
我觉得是，
但是答案只有804。
我是没有少读呀，我少读啊，应该要。
然后这个怎么样 without calculation？ 怎么样 without calculation 知道的？
就你这样子哦，你应该是看得到这个吧？看到这个不是？但是这一个也等于这一个，这样的话它是一个 non-zero solution to 这个 eigenvalue， 所以它就是它的 eigenvalue。你明白吗？OK， 这一个你 OK 嘛，对不对？然后这一个呢，这个你 OK 吗？OK， 然后把中间丢掉。这就是 A lambda A V 等于 lambda V 嘛，where lambda 等于0嘛。但是这个成立是因为它的 solution 是一个 non-zero 的，对吗？
但是这个负1、2、1这个
怎么想出来的？怎么找出来的？这个就是好像你要去解它的。OK， 怎么找到这个东西？是我去想它的 null space， 我去想它的 null space， 对吗？因为如果你做 row reduce 做久了啊，你是不是会想说，like 是不是很简单就可以 row reduce 掉？可能这2排都可以被你 row reduce 掉嘛？你 row reduce 掉了过后，也是我们只剩下一个 pivot 了。这样的话，你肯定是有2个 linearly independent 的 null space 里面的 basis， 对吧？但是你想想看，怎么造这2个东西出来？Basically， 你就是要拿 linear combination such that 这个整个东西是0，但是你看啊它重复性很高诶，有4减4诶，你要怎样把这4减4的组合加成？Obviously 可能我拿这个减这个加这个嘛，但是问题是又多出来这个嘛，所以肯定我就要多一点负嘛。但是我多一点负，但是真的又不够了嘛，真的又不够，但是哎，刚好它的 ratio 又对，比例又对，我等一下它就两个就不见了啊。然后这两个怎么会知道怎么有什么差别呢？因为你看这个2，我不一定要放在第2 column 嘛，我也可以放在第1 column 嘛。但 turns out that 这两个 vector 也是零的类。
那所以说这两个就是0的 eigenvector。
对，没有错。
那
哦，写错了，我这个改了，我已经发上去了。但是这个好像是错的，你再发给我这个这样，这是你发我的改过的。你几次发？哦，昨天晚上我还没有看到这个邮件呢。OK，我会改那个0的，那个应该有0在里面。这个有哦，放错了。
因为这个
哦，好，对。或是复试。OK，可以，好，OK，我会查一下你的邮件，我还没有看到。OK，还没有，一下子，别紧张，有时间，我们今天很多时间啊，也不至于吧？我觉得你会做到闷，我觉得你会做到闷。Before we start, actually I got some question. Jia Wei here or not? To Jia Wei. Hey Jia Wei, how do you improve in your quiz? Do you study more? You study more? Okay, how do you study? Oh, so you read lecture note and textbook together. Okay. Do you spend a lot of time studying or not? Or just few hours per day? Wednesday, Thursday. Ah, okay. I want to do some survey. How many time is enough to do good in my class? I need to give my student this timing. Okay, 思雨呢？新宇呢？I think 新宇 first time is you accident. You accident, right? So actually you are good student, is it? Okay. Because your quiz is like 5, suddenly 18, 20. Okay, why you accident the first time? Not used to it. You can't understand. But now do you understand it? Better. Okay, how do you understand it? Do question. When you did right, okay. How about Sing Tong? Sing Tong. Where's Sing Tong? Hey, Sing Tong. Yeah, how about you? Your first quiz is not very good, right? And then how you improve? 什么 Just do the tutorial question. You do tutorial question. Okay, good. In few more. 云溪, Huang Yunxi. Huang Yunxi very impressive. Go from 1912 until 19. Almost full already. How about you? How you improve? Spend more time. Okay, time is important. Time is important. How many time you spend? Most 3 hours per day. A week? Wow! 3 hours per week is enough, okay? Don't say too hard, 3 hours per week is enough, okay? 3 hours per week, Very impressive, Is Nguyen here or not? Nguyen here or not? Hey, for those who didn't come today, there's no more makeup quiz for you, there's no time.
Okay, yeah, sorry about that. 韩语呢？过韩语。Yeah, so your score from 18 to 20. So are you a good student actually? Yes, maybe yes. Okay, but how you improve? Oh, you didn't count the first way. That one is quite sad. Yeah, quite sad. That one is quite sad. Yeah, if you don't count the first way, it's quite sad. Yeah, I think it's about that. Yeah. Because improving is actually hard. If you want to go bad, is easy. Because this is life, physics. Entropy. Do you know entropy? If you things put there for long times, sure will go back one. Sure will go back if you put one things there. Especially in our university. Do you get mold or not on your things? Mold, you know mold? 发霉啊？有没有？容易坏嘛？学校的东西。Right? This is natural. But to go become better, go good is hard. Okay, you need to put in effort. Then like your friend need to put in time. Okay? Okay. So are you guys prepared or not? Please keep all your stuff. Keep all your stuff. Let them keep first. Keep all your electronic devices, your notes. Good. Keep all your electronic devices, your notes. Okay, please keep all your notes and electronic devices. No need to rush, we have enough time. I think it will be quite boring this time. So we'll have quiz until 11:50. We'll have enough time. We'll see how it goes.你等开，哇，OK，好，可以，应该可以，没事，你帮忙一整关。Why should hey, there are more there. So I want to remind you, for the first question, you can use up to the whole pages. So last time, some of you either do the core factor expansion calculation, right? So you do small. So make sure you write all your steps down. Seems like the calculation quite long. Yeah, the class extend 10 more minutes, so we will finish at 11. Now it's 10:50. So the A for the second part is from first part. Actually, there's one question only. So you see the 5 parts referring to the same thing.
3 more minutes. If you're done, please check your answer. Okay, 1 more minute. Please clean up your solution. Write your name, your ID. So if you want to see your result, please come Monday, Monday 10 o'clock to 12 o'clock to my office. I don't want you to ask me one by one in the Teams. I won't answer one by one. There are too many of you. So please come to my office if you want to know. Otherwise, I will post the solution. And then you can study from the solution. Okay. If you want to see your mark, you want to see how you do, come on next Monday in my office, 10 to 12. Okay. Please don't message me because there are 90 of you. I cannot reply everyone. Okay. So done. Tested and done. Is pass to the L. Please help me to calculate if you get the right number. The name page face up there. The name page face up. Please make sure you get the right number from your rows.
Teacher, you get the right number, yeah? 对吗？对吗？ OK， 够人吗？够人吗？OK OK。pass pass pass。pass pass pass pass。quick quick。I'm gonna finish earlier. Yeah, collect from a row. Pass pass pass. Don't discuss. Quick 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 quick. And discuss after quiz.够吗？
还有一个吗？
跟他们说，跟他们说，跟他们说。Quick quick quick. Time's up. It's 11:03 now.够吗？读的。Enough? Enough? Okay, thank you. 哪一个？第8刀的。Enough? Enough? Thank you. 够吗 ？OK。Okay. Any more? Lại. 还在算，还在算。OK。有。你说，怎么就2个？其他人啊？谁还没算完？对。How many more？
事情有点乱，
谁？
有点乱。
啊，直接有点乱。Wait. Who haven't finished yet? Haven't finished. Anyone haven't finished? Back. How many more? Benny. Benny, Lori, you guys done? How many more? How many more? One more. One more. Who else haven't finished? Just. 太难了，真的没？来，会做没时间？OK，步骤写一下比较好。答案没算出来。对。name. OK. So one thing I want to remind you again, steps is very important. Okay, at least you need to write down the step if you cannot finish the calculation. Four of you. Right. One more. Finish. Okay. Thank you. Okay. So any more? No more. So we will break until 11:15, and then we'll come back for revision. Yeah. Let's break until 11:15.
帮我算一下。
算一半，我算一半。
我们加起来看下对吗？88。
我会开错那个题目。
周末你要拍，我会发给你哦。
开始了。
哦，你要4分。好，你多少？40，我这47哦。加41呢？40，对，40，137，是，对啊，对。哎，怎么翻来覆去啊？这样呢？
I think I still receive email and question on Teams. I will reply you guys later. Later I will reply you. Unless you want me to reply now. Yang, do you want me to reply now or you can do it later? Let's see what's the question about finding orthogonal.
相当于两，它是可以同时这样做。
我已经改了，应该是对的答案。
哦，
这个答案应该是对的。
这
我想一下，错了，我好像又改了，我又改了，你看一下，我又改了。对，上次有人告诉我的错，对，又改，应该是减 S20跟 X2，然后这个是 X2。对。
然后这个，因为它的algebraic 2，但是它弄出来的 geometric 是1，所以它是没有办法。
OK，
是吗？
是，理应是，这个是我没有做过的，这我没有做过，但是我的 lecture note 有做，
lecture，但是你的
答案不一样，是这个啊，是这一题啊，
是这题，
我写什么？
这个
因为它这个只是在找 eigenvalue 跟 eigenspace，对，如果假设你要带个来，其实是那个 eigenspace 是什么？它就是这个matrix 的 null space，或者就是说，因为你看啊，你其实这个是 from 一个很简单的观察，就是说，你如果符合 ax 等于 lambda x 嘛，这样的话，你一定是符合 acx 等于 lambda cx，就是说你 x 只要符合这个 eigen 那个 equation 的话，它整条都符合，其实
相当于是 eigenvector 的一些被 melting
span of 那个 eigenvector 都是个 eigenvector 来的啊，对，
相当于它是就是这个 span 这个。
I think those who want to leave already leave, right? I think we can start. Allow me here. Okay. Are you okay with your fasting? Do you study at night? Yes, okay. Okay, let's do an overview now. See if this match with what you have learned throughout this course. Okay, so it has been 5 weeks here. Actually, this course is quite intense because MIT also do a similar course, but they do it throughout 15 weeks. But did you know that our September semester becomes 14 weeks onwards, right? Our long semester cut short by 1 week. But anyway, so let's do topic 1 first. So we'll focus on topic 1, 2, and 3, and 4. So first thing we learn is systems of linear equation. All right. So we learn system of linear equation. So inside this part, right, either it is inconsistent or it is consistent. That's why I mentioned you know all these cases. Then how do we solve it? How do we solve these system of linear equation? Basically, what we do is elementary row operation, right? Row 1 minus row 2, right? And then you do substitution, something like that. So these are actually categorized as replacement, interchange, and scaling. Okay, you can do these 3 operations without changing your solution. And then we pick out the coefficient as our matrix. So then we will go to something called the reduced row echelon form to solve your system. Okay. Why we like reduced row echelon form here? Why do we like this? Because it is unique. Okay, it is unique for each matrix. If I miss out something or you want to ask, you can just cut me. Yes, because this is unique for every matrix. And then inside the reduced row echelon form, right, what do you want to look for? What do you look for? You look for the pivot position. Okay, and then those are not the pivot position, they are the free variables. Okay, they are the free variables. And then this free variable actually gives the non-trivial solution to your homogeneous system. Okay, so this free variable gives the non-trivial solution to your homogeneous system. Okay, and then there are the important four equivalent statement about spanning. This is very important. Equivalent statement about spanning theorem. So what's this spanning theorem? This is about the every row has a pivot. What happens if every row has a pivot? The four equivalent way. And then this four equivalence way actually give you the relation between linear system and vector equation and matrix equation. And lastly, last but not least, the augmented matrix. Okay or no? Augmented matrix. Okay, after span, what did we learn? We learned linear independent. And we learn linear independent. So what's the difference between linear independent and span here? So here we will have every column has a pivot. Every column has a pivot. Then after this, we go to linear transformation. But this linear transformation is not between vector space yet. It's just between the Rn and Rm. And then we learn the concept of one-to-one and onto. So we learn the concept of one-to-one and okay. So this onto is like onto is about consistent system. Okay, so there's a relation between this. And then one-to-one is about unique solution. Okay, or the first one we will phrase it as existence of solution. Hey, these two concepts different. Existence and uniqueness. Do you ever think about it? Exist and unique is different. It's a different concept. They could exist without each other. Can you think of an example? Can you think of an example? Maybe something exists, something is unique, but exists but not unique. Doesn't exist but unique. Doesn't exist and doesn't unique. Can you think of an example? Maybe doesn't exist but unique. Doesn't exist but unique. For example, here only with salami and Abdurrahman or Hamdan here. You know there's a movie called Nerza. You guys know? There's a Nerza movie. Huh? It's a very famous movie now. You can go and watch Nerza. I don't know. Okay, let me search for you. Yeah. Okay, you can go and watch this movie. This is very famous, go viral globally or actually. It's like they call it a Chinese Marvel. Chinese Marvel. So the animation is very good actually. What that mean? But what I want to say is, Nerza could be the thing that doesn't exist but unique. There's only one Nerza, but you cannot find it here in this one. Okay, it's just like people think about it. It's a illustrated character. Okay. Does it make sense? Okay, there could be something as is, but you're unique. Are unique, yeah. So in mathematics, it's the same actually. You could prove that some solution is unique if it exists, but it could never exist, but still unique. So this is something we do in maths. Okay, some solution, if it exists, must be unique, but it could be not existing. Okay, yeah. So it's very natural in this way. Okay, I suggest you to watch this movie. It's a masterpiece, but I never watched it yet. I haven't watched it. Maybe I'm gonna watch it soon. Okay, so on to one, and then let's see. Should we do the here? Wait. Okay, yeah. So first of all, like this first, and so well in this part here. So in this part here, we will find. Let's call this linear transformation. Okay, so we will find a matrix A for T. Okay, so how do you find a matrix A for T? So A is just by adding T on the standard basis. Okay, so you see a similar pattern popping up later when we go to the vector space. Okay, so in this case here, if you have a linear transformation between Rn and Rm, but you need to remember, and maybe you need to remember one example. For example, rotation. There's only one example you need to remember. Maybe rotation in Rm. Okay, for the rotation. So maybe you want to rotate by clockwise. So clockwise by, let's say, the degree theta around 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 the origin. Let's say in RP. Okay, so well, I mean, if you draw this linear transformation, right? Let's say this arrow here. Okay, if you rotate clockwise around the origin by theta, probably you get something like this. So let's call it V and TV. Okay, but in fact, you can realize this T as a matrix. Okay, if you remember, it's cos theta minus sine theta, and cos theta. Okay, I didn't tell you how to derive this, but you can check that they do the same thing. I mean, rotation, you just take a vector and then rotate it, right? But instead, you can calculate this vector using matrix vector calculation. But I didn't tell you how to derive it. Okay, I just tell you there's a formula. Okay. How to derive this? Actually, is given by this formula here. Okay, so you need to compute what happens to TE1 and what happens to TE2. So the E1, E2 in this case here is you have to look at what happened to the vector 1, 0, and then what happened to the vector 0, 1. Like this. Okay. Yeah. So if you believe me, right? So this should be the vector cos theta and sin theta. Do you know how to plot this cos theta, sin theta? So 1, 0 is here. Let's say 1, 0 is here. And then you put it up like this. T of 1, 0. Okay, now here is the theta. So the x coordinate here is cos theta, and then the y coordinate here is sin theta. Okay. Yeah, this is how you get the trigo laws actually. Trigonometry law. Okay. Yeah, why is it cos? Why is it sine? I didn't tell you why is it, but But do you guys ever listen, like heard someone telling you where the sine and cos from? 告诉你，他们怎么告诉你的 ？How did you learn sine and cos？这三个是 ，and then the ratio between the side, right? Okay, yeah, that's right. And also that you notice that this two, because we are just rotating, right? Meaning the length didn't change. Okay, if the length didn't change, actually these two factors, right, live on the same circle of unique one. So they live on the same circle like that. Maybe this circle is not regular, but this circle is a unique. We call it unique circle with length 1. Okay, yeah. Okay. Anyway, let's continue. So basically, this is chapter 1. Chapter 1 includes quite a lot of things. Okay, how about chapter 2? Chapter 2 is quite short. It's just matrix algebra, tells you how to do. Yes? The picture? I will pause it later. I'll pause it also. Okay. I'll pause it later after the lecture. Okay, so in matrix algebra, what do you have? What can you do to matrix? You can do addition. You can do scalar multiplication. And you also can do multiplication. Okay, so this is the point of algebra. Whenever you see the word algebra, that it means these three things. You can add, you can multiply, you can do scalar multiplication. So what's the difference between scalar multiplication and multiplication? What's the difference? Both of them multiply two things together, but the two things that multiply together is different. What's the difference? Different by a scalar, right? So what's the scalar? Scalar, you should think of it as a number. Okay, number multiplied to a matrix. But multiplication is multiplied between matrix. Okay. But in the end, you still get a matrix. All right, and then in this chapter, there's one very important. Okay, I put the double T instead of D. So one important thing is called the elementary matrix. Okay, this elementary matrix is the one that realize the ERO, the elementary row operation. Okay, so this is the interesting part of this chapter here. Okay, the elementary matrices. What do you do here? Because we will introduce the idea of, what did we introduce here? We introduce determinant first, right? So we introduce determinant. Okay, and then what does elementary matrix lead to the determinant? In particular, we found out that determinant of AB equals to determinant A times determinant B. Okay. And then from here, we also figure out 2 by 2 inverse formula, right? We found the 2 by 2 inverse formula. Okay. And then we learn a little bit of subspaces. Okay, subspaces. So that's why you take quizzes on this week. You have what? Find the null space of A, and then column space of A, and then row space of A. Right? So in this chapter, we already learned something about basis, and then dimension, and then rank. We will come back again in chapter 4. So here, there's a very important theorem here. And then this theorem is very useful for your final. So I think I will highlight this chapter. Maybe you need to put more focus on this subspace. Let me highlight it. So you need to put more focus on the subspace. Okay, the rank theorem will be very useful for you. I don't ask you to prove that, but you need to know how to use it. Oh, another thing about proving, right, in my notes, right? Actually, those proof that I pick for you, right, is what I think easy for you to understand. Do you think easy or not? Or still hard? Still a bit hard. Because why is it hard? Maybe there's some small technique that we didn't go through in class. Yeah, but this technique is very standard, I would say. Yeah, yeah. Okay, never mind. If interest, you can come to MAT. Rank theorem. Next is about a basis theorem. So a basis theorem about when to get how many linearly independent linear independent and spanning vector. Okay, and then we get the idea of coordinate vector. I mean, coordinate vector, I think for sure will come up, but I don't want to special highlight. Okay. Should we go chapter 4 first? Let's go chapter 4 because these two are quite related. Shall we go on chapter 4 first, and then we will do chapter 2. So let's do chapter 4. Actually, there's a slogan on this chapter here. The slogan is our world is a model using vector space. Okay, so that's why we are fanatic about vector space. And mostly the computer language you use also built on vector space. So in this chapter, we learn what is a vector space, so the definition of vector space, and then we generalize the definition of a subspace, right? So basically, there are 4 things to check, right? Subset, zero vector, closure of addition, and then closure of scalar multiplication. So there are 4 things to check here. Maybe I don't list them down. We talk about it a lot of time here. And then next, the very, very important subspace is the span. Okay, span of any vector is a subspace. So on the right here, spans on any vector is a subspace. So that's why we have the null space, column space, row space. All these are span of certain vectors. Okay, no? Yeah. So this is a very important key to understand why you want to find basis on null space, column space, so on. Okay, even the eigenspace also a null space. Okay, so the core concept here is the span of something is a subspace. And then next, after subspace, I draw the picture to you, right? Some smaller set of vectors form a basis, because this set of bases will tell you everything inside your subspace. So basically, this is independent and span vectors that are linearly independent and span your subspace. So I would say it's basis of a subspace here. Okay, and then how do we get the basis theorem, including the previous one? Actually, this is just a spanning set theorem plus the linearly independent theorem. So what's this 2 theorem doing? You still remember or not? Independence. So if you have a spanning set, you can keep adding the linearly independent vector until you get a basis. Or you have linearly independent, different way. If you get a spanning set, you can remove all the linearly dependent vector until you get a set of linearly independent and spanning set. But if you start with a linearly independent set, what happens? It might not span your set. So what do? You include more linearly independent vector until you span your set. Okay, so this is the idea of these 2 theorems. And then both of them will add up to basis theorem. You will have a full set of basis. Okay, and then what we say is basis can change. What doesn't change is the dimension. Okay, the number dimension won't change. You can change basis. Okay, if you want to remember example is about R2. Right, R2 can be spanned by center basis 1001, but also spanned by 1011, for example. Okay, basis can change, but the dimension won't change. Okay, so that's why the dimension is very important. So in this case here, we come up with the unique representation theorem, which we use the coordinate vector. So we don't really care about basis element anymore. Actually, it's just the coefficient changing. Why not we just study coefficient? It's enough already. Because basis won't change. Okay, basis is fixed. So we just learn coordinate vector is enough. So this is the place where we get the finite dimensional V that is isomorphic to I. Okay, because we just look at the coefficient is enough. So what's the map here? This map is the coordinate vector. Let's say how B is on basis. Okay, and then after that, it comes to your nightmare. What's your nightmare? Your nightmare is the change of basis. So basically, what you do with your change of basis here, you take your C and then you arrange B on the other side. If you row reduce this to identity to some matrix, this matrix is the change of basis matrix from B to C. Or in the notes, you will say, in the textbook, you will see it as a change of coordinate basis, right? But in my class, we also call it change of basis matrix. They refer to the same thing. So please don't confuse when you go into the exam. They are the same thing. Okay? What the question used, you just follow. Yeah, what does this matrix do? Anyone remember? What does this matrix do? What does this matrix do? If you apply to a vector in B, you will get a vector in C. Okay, so this is what this matrix do. Okay, so far okay. Okay. Next, let's go back to determinant a bit. Determinant is actually quite short, right? The topic of determinant. So it's very short. There's only one thing we study here is the determinant. Yeah. So there are a few ways to get determinant here. So first way is you learn the hard way, which is the core factor expansion. And so you core factor expansion, but you can do it on any rows and columns. So this is a nice thing about it. You can do along any rows and column. And what else? And then you learn Cramer's rule. You learn Cramer's rule. Actually, we didn't do much on Cramer's rule other than use it to solve inverse. Actually, this guy can solve the problem of AX equals to B. Okay, and then only then we use it to solve more equation, which is to find the inverse of A inverse. Okay, so what's the formula of A inverse here? 1 over determinant of A times adjoint of A. And this is a generalization of the 2 by 2 case. This is a generalization of 2 by 2 case because in the 2 by 2 case, you can find that the inverse is just 1 over AD minus BC times you swapping DA and put a minus on BC. Okay, so this is a generalization. And in this topic, do we learn other stuff? Yeah, we learn invertible matrix theorem. Okay, so when is a matrix invertible? If and only if determinant is 0, is non-zero, and then you can say that this is equivalent to row equivalence to identity matrix, and then you can lead to other equivalent statement. Yeah, because you can find the inverse. Yeah. One way to find inverse is what? What's the other way to find inverse? So you put A here on one side and then put I on one side, and then you row reduce until I and something else, which is your inverse. Yeah. So it is row equivalent to identity. Okay. two more things to go. So next, I think next is the most abstract chapter, which is eigenvalues, eigenvector, because here we combine with linear transformation on abstract vector space. Okay, so basically this chapter, right, you need to remember a very important equation, which is ax equals to lambda x. Okay, then we want this x to be non-zero. Zero vector no use. Please don't put zero vector in. Okay, so this is true if and only if a minus lambda I x equals to 0. So last time I teach you one way to think about this, right? Instead of a matrix kind of vector, right, it becomes a scalar kind of vector. But, well, you can understand it as another matrix kind of vector also can. How do you understand it? Actually, it's a diagonal matrix, okay, with diagonal I times x also can. Yeah. Okay, so this is a nice thing about scalar multiplier vector. You can regard it as a matrix multiplier vector with an identity matrix. Okay, so what's the main point from here? Do we reach to a main point? Oh, not yet. So another thing is we know that the null space from here we can see the null space of A minus lambda I actually is what we call the eigenspace of the eigenvalue. Eigenspace of eigenspace of A. Okay. Yeah. So the null space of this thing is what we call eigenspace of A. Well, I mean, if you don't see it, if you put if AX, okay, if AX equals to lambda x, actually ACX also equals to lambda CX. Okay. So one vector satisfies this equation, the whole line will satisfy this equation. So it becomes a space. So the span of x will be the eigenvector also. So you just pick one is enough. And then what we know is eigenvectors with distinct eigenvalues are linearly independent. And then you give our most important theorem in this chapter here, which we call the diagonalization theorem. Okay, so this theorem for sure will come out in your exam. This one for sure. So make sure you know how to diagonalize stuff. So this one for sure you will come out. Okay. So this one for sure will come out. And what do we do in diagonalization here? We write A equals to PD P inverse. But what are the P and D here? So P are the eigenvector. So these are columns of eigenvector. D, the diagonal entries are all the eigenvalues. Okay, make sure you pair out when you pair out with your eigenvectors when you put into the column. And in this case here, what do you need to satisfy? Actually, the algebraic multiplicity must be equals to the geometric, so that you can write this out. And also, we will say that A and D are similar. Okay, if they are similar, if there exists an invertible P such that you can write it as A equals to PD inverse. So they are similar. Okay, but the question is, can we do this in a general finite dimensional vector space? Okay, so the question is, we want to do this in the general finite dimensional vector space. So the next part is we want to do this in a general vector space. We want to do this in the general vector space. So what do we do here? So maybe I do a very long ladder here. Okay, so should we do that first? Should we do this first? Okay, before we do this for general vector space, let's do the normal case first. So if we have a linear transformation between V and W, so what do we do here? Maybe we can write it as a span of B here for V, and then W, we write it as a span of C, okay, such that the dimension of V is N, and then dimension of W is M, let's say, okay? And we say that we can associate this to a matrix. What's the textbook notation you use? Matrix for linear transformation. MT. Is it MT? Do you use MT or not? What's the textbook using? M. Just M. Okay, I like MT. Because we will like, if you put M, I don't know where the linear transformation comes from. So if I put T, I know that, oh, this is the matrix associated to T. Okay, so how do we get this MT here? The story is you do the coordinate mapping here. Okay. So the concept here is to just look at what happened to the coefficient. Okay, so maybe I put a slogan here. Just study what happens to the coefficient as the bases are fixed. Okay, just study what happened to the coefficient. So through this map, right, we will send V to Rn and then send W to Rm. So basically, this is the space of their coefficient here. So how do we build this MT here? I think just now, Nuri told us, right? So what do? We apply MT to B1. Sorry, apply T to B1. And then apply T to every BI actually. But not enough, right? We need to read it in the basis of W, which is C. Okay, then this is your matrix associated to a linear transformation. Okay, but there's another second question, right? Like what Rochi asked us. So let's say now I just want to consider VV. So let's fix VV here. And let's fix VV here. And then we pick the same basis for both V. And then this V is a dimension N. Okay, we do the same story. We do the same story. I coordinate vector to Rn, and then we get the MT. Okay, in this case, let's call it A. It's just a matrix. Okay, just call it A, just a matrix. So what is this MT here? Is what we do. We check T on those E1, your E2, your EN. Then I apply on E. Okay. Right. So we got a basis here. Then what do we do? Then what do we do here? If we pick this standard basis as a span of the eigenvector, okay, we pick this basis of your ion as a span of eigenvector, then we can continue the story. Okay, we can continue this story to do diagonalization. Okay, we can put our diagonalization story into this. Okay, so we can do this diagonalization. So what's this diagonalization here? I think I do something wrong with my previous chapter. So actually, we can put the change of basis. Change of basis. Change of basis. What's this? Change of basis. Change of basis. Change of basis matrix here. Okay, so this is the inverse of what? Anyone remember? Remember? Cannot remember. So if you can, you go back and check my explanation. So this is the span of standard basis. Here also span. And then this inverse here is the inverse of E that go from where to where? Go from standard basis to eigenvector. Okay, if I'm not wrong, you can check with my previous calculation. Okay. So here is also inverse. Okay. So actually we can put all the story together. Yeah. If you cannot follow, please bring this map. Go back and look at my previous note. Okay. Lastly, very last. So it's about orthogonality. Last part about the last thing in this course is orthogonality. So in orthogonality, we introduce what? Orthogonal vector. Okay, but to talk about orthogonal vector, right, you need to know about inner product. Okay, need to know about inner product. After inner product, we will learn what's the length. Okay, what's the angle between two vectors. Okay, basically this is summarized into this formula here. U dot V equals to length of U times length of V cos theta. So U dot V equals 0 if and only if theta equals to 90 degrees. So that's why when we want to ask whether two vectors are 90 degrees each other, you just check their dot product is 0. And then non-zero orthogonal vectors. Why are we obsessed of orthogonal vectors here? Because they are automatically linearly independent. And this is what you have been doing when you draw the axis in your calculus or what? Because they are orthogonal, or they are linearly independent. And lastly, I think this is very important for you already. So you need to know how to get orthogonal basis for some subspace. Okay, how to obtain orthogonal basis. This is very important. Important for exam. And then what else is important? And then grudge myth. Okay, grudge myth is important also. Okay. Yeah. For the other things, I didn't say that they are important. It's not that they are not important, but I think the one that I said is required some revision. So you need to better revise those. For the other, please read also to make sure that you have a better picture of what's happening. But for those that I highlight, I think you need to put more effort. And then you can do more question related to this. Okay, any other question? No? Okay, if there's no more, then good luck in your exam. Thank you for the semester. See you again. 可以。
就是我们懂 subspace 啊，是我给每个空间的，然后我们的东西可以在这个空间里面去这样延伸。OK，这样子我是 use space。
Now space 啊，now space 是那个space such that now space of 一个 OK，now space 是 now space 是 of 一个 matrix，然后它的定义是说所有的 vector such that ax 等于0，所以所有可以让这个东西符合的东西，所有的 x such that ax，比如说你有1002嘛 ，OK，什么东西可以让这个 matrix 等于0？
减2等于1，我2等于
2跟1 ，yes， 不能吧？OK， 可能这个有一点不好玩，maybe 这个跟我想想啊，这个，等下你可以检查11，它会拿到00嘛？所以这个11就会活在它的 null space 里面，所有能够让它
为什么 free variable 啊找出来答案会刚好活在这个世界里面？
因为给我想一下啊，因为你在做 free variable 的时候的意思是什么？其实看你想做 free variable，你一定要 augment with 这个零 vector， 你要 augment with 零 vector 的 free variable 才会给你那个答案。因为你在解这个的时候，不是就是等于在解这个吗？你在解这个的时候，对不对？就在解这个嘛。等你要解它 solution 就是那个 free variable 的 solution 嘛，对不对？啊，所以那个 free variable solution 会给你这个。
然后那个 free variable 那个东西是它的 basis 啊，那个 basis 是在 subspace 里面的，也是在
是它的 basis 来的，
那它是 subspace，
属于是 subspace， 这个是不是 subspace？
那个 free variable 的 basis 是在 subspace 里面的 basis。
对，没有错。然后 now A 是一个 subspace，这个是 subspace，我没有修过，你可以去修看，就是那个4个条件你 check。clause under addition，clause under scalar multiplication。
就是讲你的里面的意思就是讲，我要这样走路也可以，我要这样走路也可以，只是这两个路不会撞到我的意思哦，就是不会去这样讲，不会运用到对方的那条线路的意思。
你也可以这样想，我觉得可以这样想，我可以这样觉得，对呀，可以这样想，
有没有东西
呀，可以这样想 ，yes。
OK，这样。
OK， 好，可以。呀，发现。
我就没去了。
OK， 啊，
第7章在哪？
你想什么？
第7章在
没有在。这个。
对，这个为什么 P inverse 是 standard to eigen 应该？
我有反吗？我忘记我有没有反了。
我在想，这个A 等于 PD P inverse 的话，我看的那个视频，他的意思其实是先从 P inverse 开始的话，他是从 P inverse， 然后他把基底转化到了 PDP， 那就是先是如果从 P inverse 开始看的话，就是他先转化基底到了standard basis 嘛，然后 D 是 scalar multiplication， 然后 P 的话是再转换基底，再到它原来的基底。对。所以 P inverse 不应该是 eigen 到 standard。
你说这一个反？
对。
我想想。OK， 就想想啊，这个是把 eigen 的变成 standard 的。所以其实它是把 standard 变 eigen 的反，我有错吗？因为 P inverse 是把 eigen 的变成 standard 嘛，对不对？这个合理哈。就是说 P inverse 是把 eigen 的变成 standard。then
然后再 scalar，这是它的 叫什么？就成一个倍数。
对对对对对
然后
对
P
对对，
是再把它变到
变回去
eigen space。
，standard 再变回 eigen。
这个是不是 P inverse？就这个
对
是 P inverse 的话，那是不是指 eigen dot standard？还是说这是 P inverse 等于 P inverse 等于这个东西？
没有这个东西，我就是这个的意思。所以这个的意思是从 eigen 去 standard。
对对对，但是就 P 是这个，然后它这
对
个地方是 P 的 inverse。
对对对对对对对对对对对对对对对对对对，
OK。
其实就是这个，是不是？
嗯
呀呀呀呀，其实是这个。如果不要这么乱的话，因为我为什么要写 P inverse 啊？因为我要符合这个 P inverse，我为了符合它，
哦，
因为你回来的话是 P 本身。
是的。
对对对对对，我是为了符合这个。但是如果你已经抽象到你只看 eigen 去 standard 去 eigen，我觉得这个是比较好的。
嗯
呀，只要记这个就好了，其实 eigen
OK
去 standard 去 eigen。呀，
那这个其实就是 x 是在这个 ray 里面，然后它是首先是变换基底到 eigenvector，
对
然后变换基底到
对，
eigenvector 之后再去乘以 boost
没错
standard，然后再去
，yes
变换基底再变回来，所以
yes。
这个是最终的一个结果，又回到了 eigenvector。
啊，你可以这样想，但是其实我们应该要想的是这个 T 去 A，然后再去 D 的转变。我们是在看这个转变。如果你是看 element 的话就可以了，它其实都可以跑的，它怎么跑都行。呀，可以回啊。这个，我为什么要画这个 diagram 出来？其实你是可以，就是来回的。其实只有这条线不能来回吧？这条线是可以来回，因为它是 bijection。
它只是
Yeah，
转换了基底。对，
Yeah，因为转换 change of basis 的话是 invertible 的，是 invertible 的，所以你可以这里来回，这里来回，这里来回，这里来回。Yeah，如果这个是 invertible 的话，就是全部可以转来转去了。如果这个是 invertible 的
哦，
，Yeah，
对
那你就可以每一条线你都可以来回了。
，OK，
Yes，
好的，那我理解，谢谢。
谢谢。Yes，
One question is the parts that you mentioned, are they the only parts come?
No. So those part is the part that you need to put more focus on, because I think they need some exercises, and then for the other part, you can read them and then make sure you understand, um, because it will help you to get a big picture what you are doing. Yeah. Okay.
那老师那个6到4这个还考吗？就第6到第4节那些，
哪一个？
我也忘记看了。
第六的全部有考啊？什么意思？
我感
听不懂。
就是
哦，那个 inner space 那些哈。
对什么 list sequence，就比如他们2个距离最短的是哪？这个应该不会考吧？还有就这个，这个不会考吧？就这样理解就行了，然后考试不会出现这种。
我印象好像是没有，但是应该不难读吧？但这个肯定没有，
是
这个肯定没有，这个肯定没有，这个肯定没有。但是这两个应该。
那这个如果要考，肯定还要记这个公式。
呀，是。
然后就是我根据题来理解，我想确认一下有没有理解问题，没有问题。比如说这个，这道题的话，它求的是，它的 trans 就是 t，然后它要反映的是这个 t 为1，根据这个图的话，